Okay, our second to last speaker, that's right, we're down to the last two. This is the home stretch, everybody, is Al Sweigart, who is a local to the Bay Area and is the author of Automate the Boring Stuff with Python. He's here to tell us about recursion, defining it in terms of itself, which will probably become funny halfway through the talk. Please make him feel welcome.
Am I on now? Excellent. Hello, everyone. Thanks. I'm Al Sweigart, and this is my presentation, Recursion for Beginners, a beginner's guide to recursion. Actually, this is my presentation, Recursion for Beginners, a beginner's guide to recursion. I have a lot of code and links on these slides, so instead of furiously copying them down, you can just download them from bit.ly/IndyPython2018 recursion. I'm mostly known for writing this book, Automate the Boring Stuff with Python, and I've spent several years now teaching Python, particularly to beginners, and trying to break down really complicated topics and put them simply. And I've been thinking about recursion because people think of recursion as this advanced, intimidating topic. And really, people think of recursion is hard, or recursion is confusing, or they don't really understand recursion, so recursion seems like magic. At least that's what the Google search results say. I like number 5, recursion is bad. So I've spent a lot of time trying to figure out how can we explain recursion in a way that's very approachable. So I've put together this talk, which requires no background in computer science. You only have to understand the basics of Python programming to understand this. But before I get into this talk, there is something I have to do. It's just something we have to get through, so I'm just going to go into it, and that is go through all the recursion jokes. Just get it out of our system. To understand recursion, you must first understand recursion. Ha, ha, ha. Gets funnier every time I hear it. There's the dictionary definition of recursion, which ends with see also recursion. If you Google the word recursion, the Google search results will say, did you mean recursion? With a link to the Google search results for recursion. I like my coffee like I like my coffee, recursive. I'm so meta, even this acronym is meta. And finally, there's the mythical creature, the recursive centaur, which is half horse and half recursive centaur. So from these jokes, we kind of get an idea of what recursion is. It's this sort of meta, self-referencing, dreams within dreams kind of a thing. But here's a better definition for it. A recursive thing is something whose definition includes itself. For example, this is Sierpinski's triangle. It's a recursive shape. It's a fractal. And the way that you draw Sierpinski's triangle is by drawing an equilateral triangle, and then you put an upside-down triangle in the middle of it, which forms 3 other triangles, and then you just draw Sierpinski's triangles inside of those triangles. So the definition of how to draw Sierpinski's triangle includes drawing Sierpinski's triangle. It's recursive. You can actually create this yourself. I have the code up on GitHub. It uses Python's turtle module, which comes with Python. You don't have to install anything extra to draw these shapes. But a better definition for programming is a lot simpler. In programming, recursion is when a function calls itself. So here's the shortest possible example of a recursive function. It's a function called shortest, and it only has one line, a call to shortest. And this seems really weird, like, does this even work? And it turns out, no, it doesn't work. It'll show you this error, recursion error, maximum recursion depth exceeded. This is also known as a stack overflow error. Hey, that's the name of that website, isn't it? Now, before we really dive into recursion, I really want to talk about stacks. That's the stack in Stack Overflow. I feel like recursion is really difficult to understand if you don't first explain stacks and the call stack. And this is where a lot of recursion tutorials go wrong. They don't explain this one concept. So really, if we go back to this joke, this is completely wrong. Really, if you want to understand recursion, you must first understand stacks. So what is a stack? A stack is one of the simplest data structures in computer science. It's a data structure that holds a sequence of data and only lets you interact with the topmost item. You can think of like a stack of playing cards where you can only see the topmost card, and you can only add or remove cards from the very top. We call stacks a philo data structure because the first card you put in will be the last card that you take out. You can also think of it as like a meandering conversation, like I'm telling you this story about my friend Alice, and that reminds me of a story about my friend Bob, and that reminds me of a story about my friend Carol, and then I finish that story, and I start talking about Bob again, and then I finish that story, and I get back to my story about Alice and finish that. That's also a stack. Now, there's two main operations that we do with stacks. That's adding something to the top of the stack, and that's called pushing, and removing something from the top of the stack, which is called popping. Now, Python already has a built-in stack data structure. It's the list. If you just restrict yourself to using the append and pop methods of lists, then you have a stack right there. We have some Python code right here. I have a blank list in the spam variable, and I'm pushing some data onto it with the append method, and then I pop it off. And you can see that instead of the top of the stack, it's really the rightmost side of the list. But this works exactly as a stack. So let's take a look at some code. This is just really standard, normal Python code. We have functions calling functions. We have this A function that's calling a B function, which is calling a C function. And at the start and end of each function, we just have some print calls to show you when it starts and ends. So when we call A, this is what the output looks like. Start of A, start of B, start of C. And then it goes in the opposite order. End of C, end of B, end of A. Because when we do a function call, and we all kind of know this already, but it helps to make it explicit. When we do a function call, we're not sending the program execution on a one-way trip to some other part of our program. Python will remember the line that made that function call, so it can return back there afterwards. If you've ever heard the phrase "go-to considered harmful," this comes from about 50 years ago, before we really had functions, and programmers would just have go-to instructions to send the program execution to another line of code. And this made debugging really hard to do because you couldn't really tell the path that the execution took to get where it was. So how does Python keep track of where all these function calls should return from? And it keeps track with a stack, specifically one called the call stack. You can think of back to that story with Alice, Bob, and Carol. Whenever we make a function call, we're going to push what's called a frame object onto the call stack. And whenever we return from a function call, we pop it off of the call stack. So the frame object contains local variables and where to return to, and a few other details. I'm oversimplifying a lot of stuff in this talk, but you can think of a frame object as representing a function call. And recursion is a lot easier to understand if you understand stacks and the call stack. I think the really hard thing about wrapping your head around recursion is that when you look at code like this, you ask yourself, like, well, where's the call stack? You can't really point to a line of code and say, here's the call stack, or this variable contains the call stack. It's handled by Python automatically behind the scenes. So if you want to learn more about frame objects and the call stack, you can look at the inspect and traceback modules. Doug Hellman has a great Python module of the week blog article on both of these things. So the first thing that you need to learn about recursion is that recursion is overrated. No. So recursion is still an important topic. You should learn about recursion. It's very useful and very necessary. But I see a lot of people using recursion when they don't really have to use recursion. And this is especially true for a few examples when we introduce recursion to students and beginners. There's a few examples that are always used. I'm going to cover two of them right now. The first is Factorial, and I'm going to cover why this is recursive and why it's also a terrible thing to use with recursion. So Factorial is a really simple math concept. 5 factorial is 5 times 4 times 3 times 2 times 1. 2 factorial is 2 times 1. You can kind of get the idea of how this works. So if you think about it, Factorial has a recursive nature because 5 factorial is the same thing as 5 times 4 factorial. I mean, if you do the math, it checks out. So for positive integers, you can have any number factorial equals number times the factorial of number minus 1. you can see that the definition of factorial includes factorial. It has a recursive nature. There's an exclamation mark on either side of that equal sign. So that means we should be able to write some code that does this, right? We can have a factorial function. It has a number parameter, and it returns number times the factorial of number minus 1. And this seems pretty simple. It'll work, right? No, it actually doesn't work at all. We see that recursion error again, that stack overflow. And the reason that happens is because 5 factorial is 5 times 4 times 3 times 2 times 1. But what our code is doing is it continues to go to 0 and -1 and -2. And remember, every time we make a function call, we're pushing a frame object onto the call stack. And that's going to use up a little bit of memory. So we can't do this forever, because eventually we'll just use up all of the computer's memory. And so what a stack overflow is when your recursive function doesn't stop recursing, and it keeps recursing forever, and then eventually it'll eat up your memory. Python actually has a built-in limit of 1,000 function calls that you can make without returning. This limit is kind of arbitrary, but it's big enough for most purposes. You can change it, although I really wouldn't. It's best to just think of it as, yeah, it's best if you just accept that 1,000 is the limit. OK, so we need to change this function. Here's a hint. 1 factorial is 1. So if we just check if our number parameter is 1, we can just return 1. This is called the base case. So it's the set of circumstances where your recursive function will stop recursing. And the other half of that is the recursive case, which is the code that does the recursion. Now, in every single function that you write that's recursive, you have to have at least 1 base case. Otherwise, it'll keep recursing forever and cause a stack overflow. And you need to have at least 1 recursive case, because otherwise it's not a recursive function if it doesn't call itself. So whenever you're writing code for recursion, it's a great starting point to just think, what's my base case and what's my recursive case? And make sure that your recursive case eventually hits one of the base cases. This is, so like I've explained that, and usually that's where a lot of people leave off. But some people are still confused because they look at this code and say, like, well, where's the 5 times 4 times 3 times 2 times 1? You can see that 1 multiplication operator at the end there, but like, where does the series of multiplications happen? So remember, we're dealing with a call stack here. Every time we call a function, we're putting another frame object on the call stack. So our factorial function is exactly like our ABC function, except it's factorial calling factorial over and over and over again. Just think about the call stack like that deck of cards. You can only see the topmost card. So this is what the call stack looks like when we do our recursive factorial function. So it starts in the upper left. We're setting number to 5. And in that function call, it has to return 5 times factorial 4, which means we have to call the factorial function again. So we're putting a new frame object on top of the call stack. And in this frame object, number is set to 4. Notice that there are multiple local variables named number. The number that equals 5 is still there. It's just underneath the topmost frame object. So that's another thing that people get confused on. There's going to be multiple number variables. And so in that function call, we call factorial of 3, which calls factorial of 2, which calls factorial of 1. And that's our base case. It just returns 1. It doesn't have to do any more recursing. So now we're returning, which means we pop the frame object off of the call stack. And that reveals that the frame object where number equals 2. And that one can return now. It just returns 2 times 1. And that pops off, and then we return 3 times 2, then we return 4 times 6, and then we return 5 times 24, which returns 120, 5 factorial. So I hope that diagram helps, but it's still kind of confusing. Factorial is actually a pretty bad example to introduce someone to recursion, because you have this line of code, and half of this line executes before all the recursive calls, the number minus 1 part, and then the other half executes after all of the recursive calls have returned, the return number times part. It's sort of like I'm telling you a story about number minus 1, and then I get distracted with multiple levels of other stories, and then I finally come back and I finish telling the story of how return number times that return value. So Factorial really isn't the best educational example for recursion. If you still find this a bit more difficult to comprehend, here I've sort of hard-coded several functions. So there's factorial 5, which calls factorial 4, which calls factorial 3, and so on and so on. And you can see here, like, oh, here's where the 5 times 4 times 3 times 2 times 1 happens. Our recursive factorial function is doing the same thing, except with just one function instead of separate functions. And if that's still confusing to you, you can just use the iterative version of this algorithm. Just a simple loop. It's fine. There's no reason, like recursion isn't automatically more elegant than an iterative solution. This code works, it's pretty readable, it's great. There's actually, I mean, recursion is not more powerful than iteration. There is nothing that recursion can do that you can't do with just a loop and a stack. And I'll prove it. OK, so I've shown you the recursive factorial algorithm, and I've shown you the iterative recursive algorithm. I have also created a monster, which is the iterative factorial algorithm that emulates the recursive factorial algorithm. Behold, look upon my works, ye mighty, and despair. This does calculate 5 factorial. I don't really have time to explain all the code, but suffice it to say, I've created my own call stack with a Python list. I have quote-unquote frame objects that are just Python dictionaries that hold the quote-unquote local variables. Even though there are no local variables in here, it's all global variables because I have no functions. It's just a while loop. The body of the while loop has all the same code as the body of the recursive factorial algorithm. I split it up into 2 parts. There's the part that's the start up to the recursive call, and then the second part is after the recursive call to the end of the function. And whenever I quote-unquote call the recursive function, I'm just pushing these quote-unquote frame objects onto the quote-unquote stack. And then whenever I quote-unquote return, I am popping them off the quote-unquote, am I doing that right? Yeah, quote-unquote call stack. So this shows, you can do this with any recursive algorithm, by the way. Everything you can do with recursion, you can do with a loop and a stack. There is nothing magical about recursion at all. But please don't do this ever. OK, so if recursion isn't more powerful than iteration, and recursion is often harder to understand than iteration, why should we ever use recursion? So I thought about this a lot, and I came up with an answer. And then I thought about it some more, and I came up with a better answer. Recursion maps very neatly to problems that have a tree-like structure and also require backtracking. You really need to have both of these features for a recursive algorithm to be very, very useful and elegant. Fortunately, there's a lot of stuff in computer science that involve trees and require backtracking. A tree is really just a node that branches off to 2 other nodes, and then these nodes branch off to other nodes. So it's naturally recursive. And if you think about it, a list is really just a tree that has 1 branch on each node. So lists can also use recursion as well. A maze has recursive solutions because really a maze is just a giant tree that you can, from each node, take one of several paths from, which take you to another node, and then you can choose one of several paths from that. Every once in a while, you'll reach a dead end, so you'll have to backtrack to an earlier node. This is used in a lot of pathfinding and AI algorithms as well. Your file system on your hard drive is a tree. You have folders that contain other folders. That's recursion. So if you don't have a need for backtracking and a tree-like structure, you really don't have to use recursion. When I showed you that, that example where you can turn any recursive algorithm into a loop and a stack, technically you can do the opposite as well. You can turn all loops into a recursive function, which I think is kind of madness. But recursion is not magical. It is simply another tool that you can use. And sometimes it's a tool that you shouldn't use. Like, what if we try to calculate the factorial of 1001? Remember, Python has a limit of 1,000 function calls. So if you try this, the recursive factorial function doesn't even work. It just causes a stack overflow. There is a way around this, though, and it's something called tail call optimization or tail call elimination. So this is used when you just have large problems that require a lot of function calls. If you redesign your code so that the last thing what the tail of your recursive function does is make the recursive call, then technically you don't need to hold on to the local variables because there's no code to run after that recursive call returns. So that means you can get rid of the frame object for the current function call off of the call stack, which means that the call stack never grows inside. I know in size. I know I'm kind of rushing through this. But basically what this means is that tail call optimization allows you to prevent stack overflows that would otherwise happen. But the thing about tail call optimization is that it's really overrated. So look at our recursive function. We can't use tail call optimization here because we have that number times part that happens after the recursive function call returns. So we'd have to rewrite this code so that we have that return, the return value of the recursive call. But that also means we need to add this new parameter called the accumulator, and that's really acting as a sort of global variable almost. And our base case starts looking really strange also. And all of this is just to solve a problem that iteration doesn't even have in the first place. Now, the way tail call optimization works is it's a compiler trick. Your compiler or your interpreter will parse your source code, realize that you're making a tail call, and then it does all the magic with the call stack behind the scenes. But the thing is, the CPython interpreter does not implement tail call optimization. And the other thing is, it never will. So the reason, other than that it encourages you to bangle your code, but there's another reason for it. Well, the short answer is it's simply unPythonic. The longer answer is explained in a few blog posts by Guido van Rossum. So you can't even use tail call optimization in Python. It's totally irrelevant. And there's a second problem that we always use when we're explaining recursion to beginners. And it's also a terrible candidate for recursion. And that is the Fibonacci sequence. Oh, yes, it's great. So if you don't know about this, it's a sequence of numbers. The first two digits are 1 and 1, and the next digit is just the sum of the two previous digits. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, and so on forever. You can write a function that says, OK, find the nth Fibonacci number. And this is going to be a recursive function, or it can be a recursive function, because Fibonacci has a recursive nature. The nth Fibonacci number is just the sum of the nth minus 1 and nth minus 2 Fibonacci numbers. And the base case is that the first and second Fibonacci numbers are both 1. So we can write a function like this. And it works for really small numbers. If you try to calculate the 35th Fibonacci number, that'll surprisingly take several seconds. And if you try to calculate the 100th Fibonacci numbers, that will take several centuries. And the reason is because each call to Fibonacci generates 2 more calls to Fibonacci. So it's like a hydra. Every head you cut off, 2 more grow in its place. And this means we're doing a lot of work, an exponentially growing amount of work. And worse yet, a lot of that work is redundant. Like we're making multiple calls to Fibonacci 4 or Fibonacci 3 right here. So the trick around this is to cache all the return values so that the first time you calculate Fibonacci of 4, you remember that. So in future calls with Fibonacci of 4, you can just return that cached value instead. And that prunes away this tree and removes all the redundant work. But again, that's sort of a trick you have to do just so you can solve a problem that iteration doesn't have to begin with. Now, this technique is called memoization, which your phone will always want to autocorrect to memorization, but it's memoization. We can just create a cache, and then at the start of the function, check the argument, return the cache value if it's in there. Otherwise, we'll just later update the cache. But Python is a batteries included language, so you can just use the functools.lru cache decorator, and it does the exact same thing. You can do this with any function. It's also good outside of recursion, but it's especially useful with recursion. LRU stands for least recently used. It's a very common caching algorithm. But again, that's just to fix something that iteration doesn't have a problem with anyway. So I hope I've gone and explained how recursion is not this magical code sorcery thing that only the mightiest of programmers can wield. In fact, sometimes it's a completely inappropriate way to solve your programming problems. Yeah, so let's recap. There's so much more to recursion, but I hope I've just started you off with a lot of really nice basics. The more you practice coming up with recursive solutions, the better you get at sort of identifying the general gist of how recursion works. But to recap, to understand recursion, you must first understand stacks and the call stack. This is the main reason why recursion is so confusing to beginners, is because the call stack doesn't appear in your source code, so it's easy to forget about it and easy to forget that it's there. You'll always need one base case and one recursive case in your recursive function. And function calls push a frame object onto the call stack, and returning from a function pops them off of the call stack. And a stack overflow happens when you never reach your base case and you just keep making recursive function calls over and over and over again without returning. Anything you can do with recursion, you can do with a loop and a stack. There's nothing magical about recursion. And using recursion only when you have a problem that has a tree-like structure and requires backtracking. I think backtracking is the main key there. Otherwise, it's not completely necessary. Tail call elimination and memoization are two tricks that help make recursion practical to run on real-world computers. Tail call elimination is tail call optimization is completely irrelevant to Python because it doesn't implement it in the interpreter. And that's it. That is everything I've covered. I'm really glad that I was able to get through all of this in 30 minutes. Here's where you can download the slides, and you can reach me on Twitter and at email. Thank you so much, and enjoy the rest of the conference.
Yeah, I'm here. OK, sorry. You finished quickly. Hi, Al. How you doing?
Great.
Here's a bottle for you.
Thank you.
Everybody, please thank Al Sweigart. You asked us for extra time.